Hey class, Mr. M here with a video about the properties of definite integrals. So before leaving class, I gave you a small little handout, which you should put in your little calculus paper foldable booklets. These six properties are excellent ways to understand graphically what exactly the definite integral does. Remember, the definite integral is one of the interpretations is the area under the curve, right? So I encourage you to pause the video, read over these six properties, either in your booklets or here on the digital version, and really understand what the text says, because it does a great job of explaining what the properties are. So having looked at those, let's talk about them in some detail. Formula 1 or Property 1, the first one on the list, is a very important one. The first and the fifth arguably are the most important of these. The first one says that the area from A to B, which is the way we normally go, where A is usually less than B, but almost always, where A is less than B, from A to B is equal to the area under the curve from B to A, except it's going to be negative. In other words, analytically, algebraically, all you really got to do is flip these values around, and if you do that, it's just going to be the negative of what the original area was. So why is that the case? It's good to know the rule, sure, but it's better to understand it. Well, this first interpretation, which I'll do in green, is the sum of infinite rectangles, which I can't physically draw, but I'll do some of them. Anyway, I apologize. Of these rectangles, and their bases are all delta x's, and their heights are all y values, or f of x's, right? Let me write f of x to be precise. F of x. Okay. Well, those f of x's, those y values are heights, and those are all positive y values, right? And those bases are all delta x values, and since we're going from A to B, right? We're going from A to B, therefore it should be a positive value, because all those values are going in the forward direction. So positive base times positive height is a positive area, which is why we normally get area. But when you go in the opposite direction, not from A to B, but from a bigger number to a smaller number, which for these purposes will be B to A, right? Our heights are still y values, and they're still positive. So again, we have infinitely many rectangles. Together they calculate the exact area under the curve. Well, each of these values are still f of x, and that's still positive, but our delta x's this time are going in the opposite direction. So they're not going to be positive, they're going to be negative. And that is where this negative comes from. It's the area, once again, from base times height and then infinitely summed, which gives you a negative negative base, and that produces a negative area. So even though this is in the top of the x-axis, it's a positive actual result, the integral is going to be negative based on this graphical interpretation. You're going in the opposite direction from big to small, from B back toward A, going backwards, so the value will be negative from what it was, which was positive. Okay, so the next one is here, and the next one is actually very, very simple. The area under the curve, which this part often represents, of this function from A to A, well, the picture for that is just this. From A, start there, end A, stop there too. You're not going anywhere. What's the area of this thing? 0. It's not an area, it's a line. So that's why it's 0. Property 3, very simple one, but we'll do an example with it as well. It's a very powerful formula. Property 3. Property 3 says when you have a whole number C, or I shouldn't say whole number, some number C, where C is a real number, I should add that, where C is an element of the real numbers. For C an element of real numbers, and this is true, you can basically, quote-unquote, factor out that C out of the integral, right? Pop it out and multiply it by the result. So let's see that in action. It's better to illustrate rather than just talk abstractly. So in this example, we have given if this is true. From 0 to 2, notice the direction there, is 3. I forgot the dx's. Let me politely add that in, dx. From 0 to 2, the area under the curve is 3. So find this integral right here. Well, notice a little trickeration here. They have flipped around. 0 to 2 is now 2 to 0, which is backwards from the way we normally think of it. So let's fix that first. Easy fix. It's now 0 to 2. It's not the way that it should be, right? Of 4 f of x dx, except since I've made that switch, it's going to go in the opposite direction, therefore it's going to be negative. That operation right there was just an application of property number 1. All right? I don't mean for you to write down these properties as you do these problems, but just keep in mind that's what I did in order to make that equal. And now what I can do is literally factor out, effectively, this number 4. So that's going to be equal to negative 4 times whatever I didn't factor out, which was this right here. Okay? And that was how did I do that? That was using this property right here, which we were calling property 3. Again, the numbers are just labels to help you, at first, in your first introduction to it, to understand what's going on. Okay. Well, we're given this, which is exactly what this says, right? 0 to 2, 0 to 2, f of x, okay. So this business is just 3. We have a negative 4 out there on the outside, right? So the answer is, naturally, multiplication sign there, negative 12. And there you have it. All right. This one's pretty simple as well. Notice you're adding two functions together, or subtracting. Well, as long as the limits of integration are constant, right? It's a to b in all three cases. I should say consistent, not constant. From a to b, a to b, a to b, then the integral of a sum is the sum of the integrals. Just like with limits, just like with derivatives. So here's an example. If the integral from 0 to pi is 4 for f, and 0 to pi of g is 5, find from pi to 0, backwards, of f of x minus g of x. Okay. Let's fix that backwards part first, because that's a mess. I'm going to make it negative, and that way it'll look like all the others. 0 to pi, f minus g. Just abbreviate here. Okay. Well, I have this minus on the outside, right? This property up here says the integral of a sum or difference is the sum or difference of integrals. So I'm going to split these both apart into the integral of f dx minus the integral of g dx. Well, once again, we have these two parts already. This part here in red, 0 to pi, f, 0 to pi, f is 4. This part here in blue that I'm about to outline for you is 5. What's happening in between and around? In between is a minus, around is there, and now it becomes elementary, Dr. Watson. Negative 4 minus 5, negative 1 is positive 1. Much ado about nothing just to get positive 1, but there you go. Alright, the next one is a bit of a doozy. It's very, very important. Notice the first part of our property here. The area under the curve, or the definite integral, the sum of infinite rectangles from a to b, is equal to the area from a to c plus the area from c to b. So what does that mean? Well, there's two ways to interpret this. The first way is fairly obvious, where c is smack in between a and b. Maybe in the middle, maybe not, somewhere in between. Okay, well, all this is basically saying is that the area, which I'm going to do here in red, this area right here, graphically represents this space, right? Oops. Right here. Well, this red space can be subdivided further with C. So going all the way from A to B, that's kind of a long trip. I'm going to take a little pit stop and find the area from A to C. That's this green business here. Oops. It's this business here. Well, that's not all of it, right? It's not enough. We then have to continue onwards, and I'll do this next part in orange. Actually, that's going to be hard to see. I'll do it in peach. Even harder to see. Apologies. Here we go. Do it in auburn. From C to B, well, that's just the rest of it, right? Just add those together, and voila. The orange and the green together, added, right, equals the area in the red, which is the whole thing. From A to C, from C to B, combine them, you have the area from A to B. But all of this makes the important assumption that C is included in A and B. That's where this graphical interpretation comes into play, right? This graph makes sense to us when C is between A and B. But nothing in the included information in the property says C has to be between A and B. So how does that work? Well, let's take a look at a different graphical interpretation of this rule. Here, I have placed C not in the interval A to B. It is decidedly outside. Oops. So, I posit to you, posit like P-O-S-I-T, not pause the video, but I suggest that this rule still holds true. Let me illustrate. The area we are looking for in question, this right here, is this same interval. Somehow, the other business on the other side of the equal sign must produce this red space. Okay, well, the area from A to C, which I'll do in green again, right, is more than our actual value. From A to C is all of this green stuff. Right? That's too much. How are you going to add something to that and get the red, which is what the other side of the equal sign is? But notice, the stuff here in orange is from C to B. From C to B, going backwards, which means it is equal to, to put it back in terms of what we physically understand, from B up to C, because C is bigger in this case, right? But if we make that fix, we just saw in the very first property that that should be negative, shouldn't it? So how did I go from there to there? I switched around the limits of integration, and by doing so, the first property told me that that must be negative. So that's where that came from. So really, I'm going to find the area from B to C here in orange, and I'm going to subtract. And if you take the area of the green and add it to the area of the orange, which really, we notice we actually make a subtraction, so the green minus the orange, voila, is indeed the red. So that's where this property comes into play. You can subdivide an interval A to B and find the area from A to C and C to B and combine them. And finally, the last property, very simple. It does not really matter your variable of integration so long as you are consistent in terms of your function, whether it's f of x's, dx's, f of t's, dt's, the integrals are still the same. So I'll link some videos to actually show some concrete examples of this. Your homework, which is due on Monday, that's the adjustment I made in class for this video. The homework due on Monday uses these and these properties in concrete examples, but hopefully this gives you an intuition as to why the properties are what they are. All right, I'll see you in class.